Spheres, that means that likely will be granted access. They just,
But it is good that your perimeter trip was. They are. So weird. So you are.
Yeah, I don't know what question. Great.
Oh my goodness, how great they were.
Great. We started like 5 new projects.
Okay.
So,
Yeah, if your grade is very bad, I think.
they're even interested in this non-linear, so you can people like this.
Yeah, you guys. Yeah. Who did you talk to?
We should follow that. But there is
Yeah, I mean, I think
a lot of well.
you want to do that. That's obvious.
No, this works.
Yeah.
Hello.
Pin that somewhere.
Where's Max? But I mean, like, is he not a- Oh, yeah.
Let's see. Yeah, we do. How's that? Does it work okay?
Yeah.
Okay. You can kind of hear it.
Yeah, you flipped it down. But
I
think
know,
it's still
there's
picking up
another
the
way to do
sound.
it. Okay. I guess I could take off this sweater. Yeah. And then I have a simple screen that should do a little bit better with the, I can point it upwards at least.
Do you want to introduce the speaker?
Who's actually the host? Are you?
You can.
Yeah.
Oh, it's still gonna click. Oh, there we go. Okay, I think that'll be better.
Are we waiting on?
Discover. So.
All right, yeah. So I guess then we can get started. Yeah, so this is Nina visiting from Chicago. She's going to tell us about neutrino-nucleus interactions.
Yeah. Cool. Thanks. Yeah. Thank you for having me. It's fun to be here. I will admit I'm a little out of it today. So if anything makes absolutely zero sense, just stop me and ask me to clarify whatever I said incorrectly. So this is a work looking at new physics searches in neutrino accelerator experiments. And this is a work that I've done with Shirley Lee and Pedro Machado at Fermilab, who are neutrino physicists. Okay, so a quick overview of what I'm going to talk about. So first, this is really a project that boils down to cross-section mismodeling of neutrino-nucleus interactions. So I'll just introduce why we need to worry about these cross-sections in the first place. It sounds kind of obvious, but there's some nuances to it that make it kind of an interesting question to dig into. Then I'll introduce a little bit about the current status of neutrino generators, which are used to create simulations in these accelerator experiments. And then I'll get into near detector tuning, which is the sort of experimental approach to our cross-section mismodeling problem. And you'll see that we really need to do something once we look at how well the neutrino generators actually do. And then I'll actually talk about the core of the project, which is tuning in new physics. So what we're going to do is we're going to look at the effect of this near detector tuning procedure and cross-section mismodeling on new physics searches in these near detectors. So specifically, we're going to focus on sterile neutrinos and neutrinophilic scalars. And I'll talk a little bit more about what those signatures look like. The reason we chose these is that they're two very different signatures, and our aim was to just try to find some representative new physics signatures where you could extrapolate the results a little bit to think about other types of new physics searches you might do. And then I'll just wrap up. Okay, so before we really dive into the experimental details, let's just remind ourselves of the basics of neutrino oscillations, because that's really the whole driving goal of these experiments in the first place. Of course, in the standard model, we have 3 flavors of neutrinos, but conceptually, if you're trying to understand oscillations, it makes the most sense and is clearest conceptually to start with 2. So that's what I have written down here. So your oscillations come from a mixing between your flavor eigenstates, which we're denoting by nu A and nu B, and then your mass eigenstates, which we denote by nu 1 and nu 2. And you have some rotation between the two that's defined in the 2 flavor case by this mixing angle theta. And basically what happens is you're producing these flavor states in your interactions, but the actual propagating states are your mass eigenstates. And so they can pick up different phases as they propagate, and you'll end up with oscillations between your 2 flavor states. And you can see if you just take a quick look at this, sort of your maximal mixing would be theta equals like 45. That would give you the largest amount of mixing. So if you look at your probability then that you have of an oscillation from, say you start with flavor A, and then you go to flavor B after some distance L traveled, you basically have 2 terms in your oscillation. So first you have what's basically just an amplitude term, and that's controlled by your mixing angle theta. Since it goes like 2 theta, if you have your sort of maximal mixing of 45 degrees, you get your maximal oscillations, which is probably what you would expect. And then you have your actual oscillation term. So this depends on sort of 3 quantities, but experimentally it boils down to sort of 2 important quantities. The first, of course, is your mass squared splitting. That's this delta m squared ij. And that ij is going to be 1, 2 in this case. Then you have your distance traveled L and divided by the energy E. Experimentally, when you're looking at this, you're sort of combining L and E into the ratio L over E. So if you think about, if I want to be sensitive to a particular mass splitting for my oscillations, that will become relevant at particular ratios of L over E. And so when you're designing an experiment, a lot of times we'll talk about that ratio rather than say the distance and the energy separately. So of course, in the standard model, we have 3 flavors. And part of what we can sort of employ to simplify our experimental issues is that these mass splittings in the standard model are, I think it's a factor 30. I'm not going to do that in my head, but it looks like, or 2 orders of magnitude, more or less, difference for your mass splittings. And so if you design your experiment for different ratios of L over E, you'll be sensitive to different standard model oscillation parameters. So this is our sort of 3 flavor case for the standard model. So this is the PM&S matrix. And basically you can write it as a product of 3 2 flavor mixing matrices. And of course, when you do this, your probability expression becomes significantly more complicated. But again, you can design your experiment such that you're more sensitive to particular oscillation parameters than others. And so different experiments will be probing different oscillation parameters based on their energies and their distances. Okay, so we're specifically looking at accelerator neutrino experiments. So here's a sketch basically of how it works. So they're looking to measure oscillation probabilities, typically standard model oscillations. And what they do is they use a 2-detector design. So they have what we call a near detector, which is ND, and then a far detector, which is FD. So this is a diagram of Dune, which is very easy to find online. So this is the experiment I chose as my diagram. So how does it work? Basically, you have a proton beam that comes incident onto some target. And then that creates sort of a beam of charged mesons, which will then decay into muon neutrinos. That's how you get your neutrino beam. So that's sort of happening right here. And then you have 2 detectors. So the first one that we'll focus on is the far detector, so-called obviously because it's farther than the near detector from your beam source. And that's where you're really doing your standard model physics. So it tends to be very large for the experiment that we're going to be looking at, which is NOVA. It's 14 kilotons. And this is typically placed order of a few hundred kilometers from your beam source in order to be sensitive to standard model physics. Then you have your near detector, which is the detector we're really going to be focusing on in our project. And this is placed very close to the beam source. So it has a very high flux. And another part of the idea, which we'll get to in a minute, is that your neutrino beam is unoscillated because it's so close to the beam source. And this tends to be, the goal is that it's more or less just a smaller but identical version of the far detector. And the idea is to use this near detector to reduce your uncertainties in flux and in cross sections.
Do you have to take into account matter effect?
Yes. Yeah, that's something that does get accounted for.
Wait, also, you said the neutrinos are produced by muons decaying?
No, mesons, like pions, charged pions, which primarily decay to muons and muon neutrinos.
Okay, but when the muon decays to a muon neutrino, you also get like an anti-electron neutrino?
Yeah, so you have your pion that you get a muon and a muon neutrino, and then yeah, the muon can decay and give you some amount of electron neutrinos in your beam, but it's a very small amount.
Oh, you mostly get it from the pi decay, not from the mu.
Yeah, exactly. Yeah. So your muon neutrino beam is coming from your decaying pions. Yeah. Okay. So why do we need to worry about cross sections? So it seems kind of obvious that if you want to compare your data with your predictions, your expectations based on some physics you're testing, that you want to be able to accurately predict what you would see for your data. So you would think, of course, I need to worry about the interactions of my neutrinos with nuclei in my detector. But actually, there's a slight subtlety to this. So if we write down sort of in a very idealized experiment, for example, our probability of oscillation from some flavor alpha to beta, you can write that in terms of the flux at the far detector of flavor beta, that's the one you're oscillating into, and then divide out what's basically your initial flux. So the flux at the near detector of flavor alpha. But this is not really an experimental quantity, the flux, because not every neutrino interacts with your detector. So you can rewrite this as the event rate of flavor beta at the far detector and divide out the cross section. And then you can do the same thing at the near detector with sigma alpha instead of sigma beta here. Hypothetically, theoretically, you can account for the flavor differences. There are some. You can argue whether we have a perfectly good handle on that, but assuming that you have that, then more or less this cross section actually cancels out of your probability. The basic idea is that what matters for an oscillation is not necessarily the absolute value of the flux, but the relative flux from where you started and then where you're measuring your neutrino interactions. So it looks like when you write this out, that the cross sections actually cancel out when you're doing this analysis, and you don't need to worry about it. But unfortunately, it's not quite that simple. So the reason is that we're not actually measuring the neutrino energy directly. We have to reconstruct it from our final state.
So, sorry, can I go back?
Yeah.
Just to make sure. So those are two different cross sections for two different flavors. Why do you
They are.
cancel?
So if you account for the flavor differences, you can have them cancel. And there are ways to account for the flavor differences.
Okay, so you're assuming there's some baseline cross section for charge current and neutral current.
Yeah, and then you have some modifications based on flavor, but theoretically you could account for that. Of course, if you have alpha equal to beta, then it's a more direct cancellation.
Yeah, of course.
For an analysis like muon neutrino survivability, then that would be more direct. Yeah. So it turns out that doesn't end up mattering anyway, because that cancellation is not going to end up holding up. So we can't measure the true neutrino energy. We have to reconstruct it from the final state. So for our NOVA analysis that we're going to be looking at, we're looking at muon neutrino survival. So you end up with the muon in your final state. So basically what you have is you're going to add together the energies of your final state to reconstruct your original neutrino energy. So for the muon, the reconstruction is pretty good. You have about a 3% resolution on reconstructing its energy. The real issue comes in with the hadronic sector of the final state, because you only have about a 30% resolution on that for NOVA. It's just much more difficult to reconstruct. For example, if you have neutrons, those are not actually visible to the NOVA detector. So you have to do sort of some statistical reconstruction to figure out what your energy was. So this is a real problem because oscillation probabilities depend on the true neutrino energy. But what we're actually seeing is the reconstructed neutrino energy. So there are sort of two ways to approach this to try to extract oscillation parameters from your data. So the first is to generate a simulated true neutrino energy spectrum and input an oscillation probability into that, and then smear it based on your knowledge of your detector into a reconstructed neutrino energy spectrum and compare with your data. So in this process, you're kind of doing a fit where you'll input different oscillation probabilities and then see which spectrum best fits your actual data. The alternative is to try a slightly more direct approach. So what you do is you take your data in reconstructed neutrino energy and you try to, quote, unsmear it into true neutrino energy. From that, you would be able to directly conclude the oscillation probability in true neutrino energy. The problem with this approach is that when you go from true neutrino energy to reconstructed neutrino energy, you actually lose information. And so the opposite process is not mathematically well defined. So there's a real art form to, quote, unsmearing or unfolding the spectrum. But since it's not mathematically well defined, it's a real art form. And it's quite difficult to do successfully. So typically experiments try to avoid this. And what they'll do is take the first approach. So this is sort of an interesting aside, if you want to call it that, but just to delve into the first approach a little bit more, I think it can illustrate some of the difficulties that come into actually performing one of these analyses. So again, this is the case where you're predicting some true spectrum, inputting an oscillation probability, and then turning it into a reconstructed spectrum that you can compare with data. So on the left, we have the event number at the far detector divided by the near detector. And you have quite a lot of new terms relative to what we had in our idealized experiment. So for one thing, you have a constant here that just accounts for your different detector sizes because your near detector tends to be smaller. You also now actually have a flux difference between the far detector and the near detector. Basically, the two detectors cover different solid angles of your neutrino beam. And so that actually turns into a slight difference in the energy spectrum of your neutrinos. You also have this migration matrix. So this is the matrix that takes your true neutrino energy and gives you a reconstructed neutrino energy spectrum. And then finally, you have your probability right here. And then you have your cross sections. And the point to note here is that your cross sections are showing up in an integral, and what you're actually seeing is the result of an integral. And they're not going to cancel each other out in this case. So if we're thinking about doing one of these analyses, unfortunately, in the end, we do have to be able to calculate these cross sections successfully. The better we can calculate our cross sections, the less uncertainty we'll have in our final oscillation parameters.
But you say that sigma B can cancel sigma A, right? So then those two integrals will be roughly the same.
No, there's a good amount of difference between, say, your migration matrices can actually be different between the two detectors. Your fluxes are different. And of course, you have the probability.
The part coming from the cross section will be the same.
It's,
You were canceling it before, right? You had sigma beta, you corrected it with some alpha dependent factor.
yeah, but it's convolved with the factors that are
Yeah.
also energy dependent. So it doesn't directly cancel out.
No, I'm not saying it cancels.
Yeah.
I'm just saying the two integrals are up. Same or not?
The probability will drive quite a large difference. So I'm not going to draw it, but at the near detector for Nova, it's pretty much a classic Gaussian. At the far detector, you have a very large dip sort of right in the middle of that Gaussian. So they come out pretty different. Yeah.
But maybe kind of going off that. So like earlier you said that, oh, I can just cancel out the factors because flavor differences aren't that big of a deal. Are you saying here I can't cancel them basically because the detectors are so different?
Well, they're in an integral, and they're combined with a bunch of factors that are quite different.
Yeah, I think the first one is a bit simplification, but here, even if I say alpha equals beta, right? So here the P matrix is you're doing disappearance experiment, right? So your alpha flavor and the flux will differ for different energy. That's what make that you have to come up with the whole thing with this E-dependent probability stuff that make you have to do the convolution.
Yeah, you have to.
So So I think really the energy dependency in P makes things complicated.
It does, yeah.
If there was no dependence on flat, I think there's a lot of cancellation.
Yeah, yeah. Yeah, everything in these integrals is dependent on the true neutrino energy, and so you do have to do that. Yeah.
It's really because P has energy.
The main question, suppose there are some heavy neutrinos, and you already see oscillations in the new detector. So where would they go in this denominator?
Sorry?
So if there are heavy neutrinos and you already see,
Yeah.
or you're supposed to see oscillations in the near detector, right? Which means that in the denominator, you should include P presumably already. But if you don't do that, if you assume that there are no such states, then where would this effect go effectively? What would it
Yes,
define?
it does sort of break the approach, and that's a part of our concern with this project. So what you're doing here is you're sort of assuming that your detector has a completely unoscillated flux, right? So that the rate at the near detector is basically your initial flux. So you're exactly right that if you have some oscillations already appearing in the near detector, you're no longer able to use your near detector as a measure of your original unoscillated flux, and you would definitely have to modify this approach. Yeah. Okay, I'm gonna keep moving if that's all right. So we have to include cross sections in our analysis of these spectra. So what we can ask is, how good are we at calculating these cross sections? How well do neutrino generators do at correctly predicting data? So one way that you can test this is actually to look at electron nucleus scattering data, because you can actually measure the energy of your electron. So here we have just a couple examples of a comparison with Gini and some electron nucleus scattering data. So Gini is going to be the solid black line, and then of course the data points are the data points, and it's the same thing over here. And we can see that it disagrees pretty strongly with your data. And that's, I mean, particularly this one, it disagrees basically everywhere. But this one as well, at higher energy transfer, you can see that it disagrees pretty strongly with the data.
Can you explain the jargons here, the QE, MEC?
Oh yeah, sorry. So these are different processes. So this is quasi-elastic, meson exchange current, resonant pion production, and then deep inelastic scattering. So yeah, I'll come back to sort of the processes in 1 second, actually. You can look at E4 new. This is basically an experiment that was designed to look at this. Here, what they have is actually two different versions of Gini. So this solid line is one sort of tune of Gini to particular data sets, and then this dashed line is a different tune. And again, they disagree with the data, and actually even within a single generator, you can get pretty strong disagreements with your predictions. And then the last one I want to look at that I think is the most interesting to me is a comparison of two different generators with the same data set. So these are two entirely different generators. This is a recent version of Gini, and this is a 2021 version of Gibu, which is just another neutrino generator. And again, both of them don't model the data particularly well, but also I think what's interesting is that, again, they disagree strongly with each other. And if you look at the different processes, you can see that the predicted contribution from the different processes also disagrees. So there's quite a lot of disagreement going on here between the data and also between different generators. What I will note is that these neutrino generators are designed to fit neutrino data. So they do a better job with neutrino nucleus scattering than they do with electron nucleus scattering. But the idea of this test is that if we're getting the physics right, we should be able to model this data successfully. And we can see that we're not. So there's quite a lot of cross-section uncertainty going into these experiments. Okay.
Sorry.
Yeah.
What we need is a neutrino-nucleus cross-section being correct, and those generators to do that. But if you replace neutrino with electron, hoping them to give you a correct result,
it's not.
It was written uncarefully. It's okay to get wrong results, right? So,
it is. The problem is that. So ideally, what we want is to get the underlying physics correct when we're doing these generators, right? And this is just a test of how well are we getting part of that physics, right? So the problem is that we know we're not modeling the neutrino-nucleus interactions perfectly. There's a decent amount of uncertainty. And so this is a test just to say, like, we can tune to the experimental data, but how well are we actually modeling the underlying physics that's driving that data? So this is a test of that. It's certainly true that, like, you would not use this generator to analyze, in some physics sense, electron nucleus scattering, but it is one test of a part of that calculation that's going into the neutrino interaction.
Actually, I forgot the essence of the Gini. Is Gini this general particle material interaction simulator?
It's
Or it's a special tune for neutrinos?
it's for neutrinos with nuclei, I think. Yeah. Okay.
But does this uncertainty come from the fact that we have form factors and we don't know coefficients precisely, just to understand the difference explicitly? Well,
That's some of it. Yeah, it's probing non-perturbative sort of nuclear protonic physics. It's quite difficult to do.
Yeah, so back to my firm, I have a colleague, probably your collaborator, told me the nuclear form factors need to be calculated or implemented correctly. Nuclear physics community don't care about that. So
Yeah.
in principle, they can solve this problem for us, but high energy physics community, we cannot we don't know how to calculate nuclear form factors.
So nuclear form factors are the input in this.
Yeah, because I'm scattering my neutrino to nucleus.
Yeah.
Are these different form factors than would enter in like a heavy ion collision? Like why is like the LHC people do like ion scattering calculation?
Mhm.
Why is this like harder than that?
That's a good question. I don't know exactly the answer to that.
If I can guess, if I'm allowed to guess, which I'm not responsible to my answer, is I think there are quite a few shared form factors, but it's still different, still different set. I'm not responsible.
Okay, so just to make it more clear, so electron nucleus form factors are not known perfectly, I mean theoretically, or not measured perfectly, and also neutrino nucleus form factors are not measured perfectly.
Yeah.
And if we tune our code to neutrino nucleus form factors, and then we use it for electron nucleus scattering data, we see more disagreement. Does it mean that there is something wrong with the code itself, or where does this additional disagreement?
Yeah, it means that the simulations are not getting the actual physics right, the underlying physics, because the electron scattering depends on a particular piece of the calculation and not the whole thing. So if you think about like maybe the neutrino calculation does reasonably well at modeling neutrino data, but it's not getting the different pieces correct, if that makes sense. So if you then focus on one particular piece, you find that in fact you're not getting the physics.
Only some, parts of matrix element, but not all of them, roughly speaking.
I think one should realize we don't have infinite precision on any of those measurements. So any measurement we have is a finite precision process. We try to fit the finite precision by assuming a certain adjust on different form factors, which may not be correct.
No, but I would like naively assume that electron nucleus form factors should be known better, right? Simply because it's, but then you implement them and you see that the disagreement is worse, which means that there is something apart from form factors, right? That is.
Yeah, I cannot compare whether worse or
No,
better.
but,
You can call the people who tune that are not smart enough.
Okay.
I'm gonna keep going. Okay, so I think we can agree that we have to worry about this mismodeling somehow. So this is what near detector tuning is designed to do. So the basic idea is that you know that your generator is not a perfect model of nature. It doesn't perfectly model neutrino-nucleus interactions. And that's really what the near detector was designed for. So the idea is that you look at your near detector data and you adjust your neutrino generator, whichever one it is that you choose. You do some process that I'll get into in a minute. And you do your adjustments such that after you've done this, your near detector data and your simulation match reasonably well. And the inherent assumption in this process is that your near detector has a standard model and unoscillated flux, because what you're trying to do is get a generator that models standard model neutrino-nucleus interactions. And for just pure standard model physics, this is a reasonable assumption because your mass squared splittings are, say, 10 to the minus 3 v squared or lower. And so your near detector, which is typically placed about 1 kilometer from your beam source, is just not experiencing any standard model oscillations yet. It's much too short of a baseline in order to see any of those standard model oscillations. So that's an important inherent assumption going into this procedure. So we're going to be following NOVA's tuning procedure because they published their tuning procedure very clearly, and very few experiments have done that so far. So first, they make a couple of changes to the base version of Genie that they use based on some other experimental results. So this is not actually touching their near detector data yet. And for our purposes, therefore, this is not the part that we're actually particularly worried about. But this is just a list of what they do. So they're adjusting the axial mass input value based on some other scattering data. They're adjusting the nuclear momentum distributions based on some Minerva results. And then they're also reducing the non-resonant single pion production based on some bubble chamber data. So these are just changes that are made based on other experiments. And you don't need to worry about these, but I'm just listing them because after you apply those, you still find some discrepancy between your near detector data and your simulation. So these two lines, the dotted black line and the solid red line, are just two different versions of your meson exchange current. So that's just two different ways of calculating your meson exchange current. And you can see that both of them disagree with the data, particularly at low visible hadronic energy. And it's probably a little bit difficult to see, but there's actually it over predicts at higher visible hadronic energy. And this is true for both neutrinos and for the anti-neutrino beam. So the basic approach from here on out is that they're going to assume that the entire rest of the discrepancy is due to mismodeling in the meson exchange current process. So this is kind of the rug under which all of the rest of the mismodeling will be swept. And what they'll do is they then adjust that meson exchange current contribution so that your simulation matches the data. So in particular, how they do this is they bin their simulation into a 2D plane. So this is true momentum transfer from the neutrino to the hadronic system. And this is true energy transfer. And so what you end up with is about 200 bins here. To each of those bins, you reweight your mech cross-section. So you can see it goes from 0 in the regions where the simulation is over-predicting, all the way up to 5 in the region where your simulation was under-predicting. Then they apply these weights and they migrate it into a reconstructed quantity. So now you have a 2D plane of reconstructed Q and Q naught so that you can compare with the data, because the data is always in reconstructed quantities. And so basically what they do is they adjust these weights and they do a fit such that they choose the weights where your simulation in this 2D plane best matches the data in this 2D plane.
So just to clarify, so yeah. Here we are modeling interaction of neutrino beam with a near detector, right?
Yes.
And we are supposed to know the flux of neutrino beam produced. And you said that there is some disagreement in the modeling and actual data, but maybe,
could that be from flux?
Part of it comes from the fact that we don't know the initial flux explicitly.
Yeah, so they do a separate flux tune. I think it comes from, I'm not an expert on the flux tune.
I assume the flux tune would have much more control than here.
So you know precisely how many neutrinos.
So you know up to some level of uncertainty, and some of the experimentalists have commented that what you really want is the full error matrix that includes the flux uncertainties when you're doing this. So it tends to be anti-correlated.
But if you know the flux so well, then why do you need a detector at all?
Oh, well, you want to measure neutrino-nucleus cross-section
Yeah.
differentially, correct? You need to be able to know the cross-section. Then,
Yeah.
because your eventual observable is the convoluted probability
Yeah.
ratio.
Yeah. So I mean, if you just look at
The picture
these spectra,
That's your detector.
these clearly do not agree. And the goal is to get your simulation to match the near detector.
Actually, they don't need to be the same experiment, right? You can measure it separately.
Yeah, so I think all we need to extract is the sigma with energy dependence, correct? Okay.
That's
So,
the goal of this
Yeah, that's
process.
the
Yeah.
goal. So, yeah.
My impression was that the new detector is needed to know the flux business. And here it's like.
They do also use it for that
not to know
sometimes.
the flux, but to know
Yeah, so
cross sections.
this is the cross-section part of the tune. They do also tune the flux separately. And it depends a little bit on the experiment, how they approach it.
Why did they shove all the rest of this modeling into MEC specifically? Like, I would think like deep inelastic scattering might also be kind of complicated.
Yeah.
I don't understand that.
It's a good question. I don't know exactly how they landed on mech. It is also a difficult process to model. And I think at a certain point, you just have to choose, I'm going to adjust this and go for it. So they call it in their tuning paper, they call it 2B2H, 2 particle, 2 hole, as more of a catch-all term for any additional interactions that haven't already been accounted for. So I don't know exactly how they ended up saying, I'm just going to tune mech. But that's just sort of their catch-all process that they're going to be adjusting.
I think if I may say, I think it's a reasonable choice because first, let me come back to the energy uncertainty. First of all, I know my initial pion flux differentially very well. I know how pion decays, so I'm supposed to know the neutrino energy distribution very well. But then how this neutrino energy distribution scatters with my nucleus and give me what's the effective Q in my system that I measure from the Q harmonic. That is what this trying to model. And then why they decide to shift into Mac? Because in some sense, deep inelastic scattering is well understood. Right? We did so many DIS measurement using electrons in a regime where the Platonic model works. I think things are precisely determined. Is that the lower energy regime where the maximum form factor are important? I would naturally shift that. So,
Yeah, I think
so,
mech is a reasonable choice
Yeah, I
in
think
terms of how well we understand it. Yeah.
Are you saying like nuclear physics is less well understood than like QCD?
Yeah, indeed, precise. Actually, that's why I built the EIC to study more nuclear physics.
Okay, I'm going to keep going because I think I'm going to run out of time here. So the basic idea is you're applying these weights in each of these 200 bins, and then at the end of it, your simulation matches your data much better. I do not know what's going on in this lowest bin. I don't think Nova knows what's going on in that lowest bin either. But other than that, your simulation matches the data much better than it did before performing the mech tune. So this is the tuning procedure. So now we get to the actual new physics part.
Sorry, I did the Mach tune for Nova data. Of course, I will get a much better fit because I tuned for that data.
Yeah, that's basically by construction, exactly.
Right. So it doesn't guarantee if I use the same tune for another experiment, it will reproduce the data. Probably they will mismatch quite.
Right. This is so a near detector tune is not something that would be used in another experiment. It's really specific to that experiment. Yeah. Okay, so near detectors and new physics. So a lot of people have proposed looking for new physics in near detectors. And there are a couple of reasons for this. The first is that it's very high intensity. It's a detector that's placed very close to the beam source of a neutrino beam. And so you have very high intensity. And because new physics typically has low rates, in order to get around existing bounds, you kind of need high intensity to get any real event rate. You also have a weakly interacting background. Your primary background is going to be neutrinos. And finally, of course, these are detectors that are already built or are already being built. So it's a really nice way to, at least hopefully, try to take advantage of existing experiments and get a lot more new physics out of it. So these are just a couple examples of models that people have proposed for near detector searches. So you have your EV scale sterile neutrinos, for example. You also have neutrinophilic scalars, which I'll briefly introduce in a few. You can also look at tritium production and see if there are any BSM contributions to this process. You can also look for light dark matter that gets produced in your neutrino beam.
Correct, but you just said the sterile neutrinos spoil the entire approach and nothing is applied.
Yeah, that's really part of the problem. So the near detector procedure, near detector tuning procedure will then get applied for a standard model analysis. That's how they account for their cross-section mismodeling to some extent. What we're talking about is a near detector analysis, where you then have to decide, how do I account for cross-section mismodeling if the whole process was defined such that there was no new physics in the first place? So we'll get into it. Maybe when we get into the analysis, you'll see.
Directly on near detector. They're not trying to see the oscillation probability measurement that Nina mentioned earlier. So-
Yeah, we're looking at just the near detector for these analyses. Okay.
So the EV
Yeah.
scale, that's dark matter, that's for the dark matter, or
EV scale is primarily inspired by the short baseline anomalies, which I'll talk about really briefly in a minute. Yeah.
it's not in the dark matter window.
No, I think cosmologically that's ruled out pretty strongly. Yeah. Okay. Great. So we do have to worry about cross-section mismodeling as we've been seeing. And so you kind of have two general options for a near detector search. So the first is you don't perform any tuning procedure like we just looked at, and you just kind of leave the mismodeling alone to potentially skew your interpretation of your data. The second option is to perform some kind of tune like that Nova-Mech tune. The problem is that you risk tuning away the new physics, because the definition of your near detector tuning was you were saying, this is my standard model, right? The near detector is my standard model. And if I'm then adjusting my expectation to match what I see at the near detector, I risk tuning away my new physics at the near detector. So these are the two potential approaches that we could see. And what we're going to do is analyze what happens when you take each one of those. So we're going to focus specifically on EV scale sterile neutrinos and neutrinophilic scalars for their particular signatures. And what we're going to look at is how the interplay between your near detector tuning procedure and cross-section mismodeling might interfere with your ability to do a new physics search in this near detector. Okay, so here's our process. So we generate two standard model simulations using neutrino generators. So we'll use Genie or Neuro. Those are just two neutrino generators. And then we inject new physics into one of them to create a set of mock near detector data. And then you have two options. So the first is just to examine the new physics signature directly without doing any tuning. The second is to actually perform that Nova-Mech tune of your model to your mock data, and then examine the new physics signature after performing the tune. And then we're going to compare the two and see how well we do with a new physics search. Okay, so let's start with sterile neutrinos. So a couple of short baseline anomalies in neutrino experiments have pointed towards the potential existence of a sterile neutrino on the EV scale mass that's mixing with the standard model neutrino flavors and mediating shorter baseline oscillations than you would expect in the pure standard model. And Fermilab has basically a whole program that's examining the possibility of sterile neutrinos. So these here are just the mini boon excess, the mini boon low energy excess, and then LSND, which is another one of those short baseline anomalies. So if you have an EV scale sterile neutrino, what this does is it induces oscillations around a ratio of L over E about 1. So the signature that you're looking at is, here we're writing down the muon neutrino survival probability. And at short baselines, you can approximate this as sort of a 2-flavor oscillation. So you're modifying what in the standard model would basically be 1. There aren't any oscillations yet, with what's basically a 2-flavor oscillation. So you have your sort of induced muon mixing angle. It's kind of weird notation, but sort of like your muon survival probability angle. And then you have your new mass squared splitting with your standard model eigenstates, and then of course your usual ratio of L over E. So what's interesting about this for the near detector context is that near detectors are actually very well placed in terms of L over E to be sensitive to this type of oscillation. So for example, for NOVA, which is the experiment we're looking at, your neutrino energy spectrum peaks around 2 GeV, and your near detector is placed approximately 1 kilometer from your beam source. So this is something that would be able to probe EV scale sterile neutrinos. So here, what we've plotted in blue is the muon neutrino survival probability for a choice of mass squared splitting of 5 EV squared. And then we chose a very large mixing just for visual sake of 0.2. So this is the oscillation signature that we're going to be looking at for our near detector.
The detectors that saw this anomaly, were they also doing muon, like muon neutrino operations?
So these are actually electron appearance here. So this is electron neutrinos here. But what you can do is you can also look for the disappearance that would induce in your muon neutrino beam.
Okay, but I mean, so they're looking at a different mixing angle though than what you're looking at.
Yeah. So you can write down this mixing angle in terms of the mixing between the muon and electron neutrinos and the 4th eigenstate. And so we didn't choose exactly the parameters that would give you the short baseline anomaly. We just chose relatively large mixing to see exactly how much the tune might wash out the signal. But yeah, if you have an electron appearance from a muon neutrino beam, you'll have some muon disappearance as well in a sterile neutrino model. So that's what we're looking at for NOVA specifically. Okay, so this is our first analysis. So the first thing we do is we use the same generator for both model and data. So what this means is that the only discrepancy between the two is the new physics. So of course, this is not yet a realistic analysis because we know that we don't have a perfect model of nature. But what it does is it gives us a conceptual picture of exactly what the tune is doing to that new physics signature on its own. So the bottom panel is really what you want to look at. So you can see the oscillations that we were sort of plotting on the previous slide. So we have 2 lines here. The first is the mock data divided by the standard model. And then the second is the mock data divided by the tuned standard model. So to get this, what we did was we went through and we did the NOVA mech tune, and then we used that as our quote standard model simulation. So you can see as you actually keep your oscillation signature, what the tune does is it just shifts it vertically. So we're not actually completely tuning away the new physics when we do this tune, which is quite interesting. We'll get to why in a minute. But the second thing we can do is look at the case where we use different generators. So the idea behind this is to use the difference between generators as a proxy for the difference between a particular neutrino generator and nature. So this gives us some sense of if you have some mismodeling, we don't know exactly what it is, how well can you do at a new physics search? So here again, we have our 2 lines. Again, this is the untuned case, and then in the red is the tuned case. And once again, we see that our oscillation gets a little bit less smooth because of generator mismatch. But you can see that the oscillation is there, and before and after the tuning, that oscillation signature remains. Again, what's happening is a vertical shift. One thing to note, though, is that if you just take your 2 out-of-the-box generators, sort of your standard model mismatch between the 2 generators, you can see that that disagreement itself actually looks a little bit like a sterile neutrino oscillation. And so we can see some hints that this mismodeling is going to bias our interpretation in this new physics context. So before we get to that, though, we can ask why we're not actually tuning away this oscillatory signal. And the reason is basically that neutrino energy isn't directly correlated with the tune parameters. So remember, the tune was being performed in this momentum and energy transfer plane. And in fact, the neutrino energy is not correlated perfectly with these 2. So here what I have is the sort of a heat map of the events for a range of 0.5 to 0.6 GeV for neutrino energy. And then we take a very different energy range, say 2.9 to 3.0. And you can see that there's quite a lot of overlap between these 2. They're not exactly the same, but there's quite a lot of overlap. And what ends up happening is that your oscillatory signature in neutrino energy does not translate to a shape in the neutrino plane. Basically, what you end up getting is an overall flat normalization change. So that's why we see that vertical shift, but the oscillatory signature still remains. Okay, so what we decided to do is a sensitivity analysis. At least given the information we had, we did the best analysis we could. So what we do is we're taking sort of the same approach that some other experiments have taken in their sterile neutrino analysis. So we do direct fit to the near detector and the far detector rates. We're doing a chi-squared fit, and we have a covariance matrix with certain systematic uncertainties. This is where it would be really helpful to have the full sort of systematics from the experiment, but we weren't able to get those. So we chose some systematics that we thought were at least reasonable to do this analysis. So this is what we end up getting. So we have three regions here. So the gray region is the case where we use Gini for both the model and the data. The idea being that this would sort of be your true sensitivity region if you had a perfect model of nature. And then we can compare with the case where we have a proxy for cross-section mismodeling. So here what we do is we use Gini for the data and Neuro for your simulation. And so in the blue is the case where you don't do any tuning and you just compare directly. And then the red is the case where you first do the Nova-Mech tune and then you compare. Although I should note what we're doing here is really a simultaneous fit and tune. So the idea being that hopefully your tune will account for the standard model differences, and then your new physics signature will fit whatever remaining discrepancy there is. So that's the idea behind that curve. But what we can see is that if you don't do any tuning at all, actually rule out the input parameters at 2 sigma, and you're skewed towards larger mixing, which sort of lines up with what we saw with the fact that the two generators sort of already disagreed with a slight oscillatory shape. So it prefers more oscillations in the untuned case. In the tuned case, it's skewed towards slightly larger mass squared splitting. I'm not 100% sure why, but it is. But at least it includes your input parameter at 2 sigma.
Sorry, I'm confused.
Yeah.
Why do you have near detector and far detector rate here? I thought you were trying to look for it directly at a near detector.
Yeah, so in I think it was Minos. The way they do it is they fit the near detector and the far detector simultaneously because the two detectors have different signatures from a sterile neutrino, because in the near detector, you do have the oscillations. And then in the far detector, you basically just have sort of a flat shift because those oscillations average out. So your real shape is showing up in the near detector. And like we were saying earlier, the whole assumption of a near detector tune is that you don't have any new physics. But they do also include the far detector. How much that really contributes to your fit is questionable, but they include it in their analysis. Yeah. Okay, so that's the 5eV squared splitting. We also tried a different mass squared splitting to see what would happen. And the situation is more or less the same for the untuned case. So the allowed region would be to the left of this blue line. It again excludes the input parameters at 2 sigma, but now the tuned line also excludes the input parameters at 2 sigma. I think one thing to point out here is that your sort of skew or your bias is not consistent between these two. So if you had a consistent bias that you would be able to account for, it would be easier to do this analysis. But the bias really depends on your true new physics. So it's not something that you can just consistently account for in your analysis. Okay, so that's the sterile neutrino. I'm going to have to blast through the second case. So basically, we're not tuning away the new physics signature, but cross-section mismodeling is skewing our interpretation of the data in terms of the new physics. Okay, so let's look at the mononeutrino case. So basically, for time's sake, what you end up with is this new neutral scalar phi interacting with neutrinos. And this could be a neutrinophilic dark matter portal, for example. In terms of the phenomenology, basically what you have is you have an incoming neutrino or an anti-neutrino from your beam. It'll radiate off of phi and then become either an anti-neutrino or a neutrino. And then it'll interact with your detector, and you'll end up with what appears to be sort of a wrong sign lepton relative to your beam mode, because this converts your, in this diagram, anti-neutrino into a neutrino. So that's the basic phenomenology. And so what you would expect, since you're radiating off a neutral particle that's not visible in your detector, is that you end up with more missing transverse momentum in your events. So that's the signature that we're going to be looking at. If you compare sort of your basic standard model predictions from two different generators, you can see that the new physics signature down here is a couple orders of magnitude lower than your background. So if you want to look for this, you're going to have to do some final state cuts. And that's really part of why we're looking at this signature specifically. So the real question for this case is, how do you approach tuning and final state cuts? Because you basically have two options. You could tune before you apply your cuts, or you could tune after applying cuts. And it's not necessarily obvious which approach you want to take. So for our analysis, we consider the anti-neutrino beam, because in the end, what you get is a proton in your final state. And that's much better for nova because nova can't see neutrons. So we don't want our final state to include a neutron. It just makes the cuts much more difficult. So we cut on one proton, no pions, and then no visible neutrons. So we say that maybe you can't reconstruct the energy of a neutron, but if it has an energy greater than 100 MeV kinetic energy, then you could at least say there was one, and we're going to cut on having no visible neutrons. So the question we're asking here is, how do cuts affect the tune's impact? And for the sake of time, I'm going to get to the actual mismodeling part. So here's the real takeaway of this part. So if you use the same generator, you find that actually you have pretty good sensitivity to this new physics. So in the case where you have a perfect model of nature, you can search for this new physics quite successfully. The problem is that our generators respond to these final state cuts very differently. So this mismodeling becomes a huge issue when you're applying cuts on the final state. So here again on the left is sort of our distributions without cuts. And while they may disagree sort of on where the peak is, they agree sort of on order of magnitude number of events in your distribution. Then you apply these cuts and they disagree quite strongly. So in the blue, we have our Gini after applying these cuts. And then with the black dots, we have Neuro after you apply these cuts. And what you can see is that this discrepancy between just the two generators is larger than your new physics signature. And so this is quite an issue if you're trying to do a search for this new physics, because your cross-section uncertainty is basically completely dominating over your new physics signal. So what we have here in the gray and the black dashed lines are two potential approaches to try to address this mismodeling. So the first is where you tune before you cut. And this does not adjust, it doesn't reduce the discrepancy such that you could actually see the new physics. And then the second approach is where you tune after you apply the cuts. And again, it gets closer, but this is a log plot. And so your discrepancy is still larger than your new physics signal. So if we're thinking about what's going on here, basically what you're doing is you're cutting to corners of parameter space. So these generators predict different cross sections for the different processes and also different final states. So the generators have different final state interactions. And so they will predict different particles in your final states. If you're applying a cut on that, you're going to see them react quite differently. So if you recall, here we have our comparison of generators. And you recall that the processes themselves were different. So if you're cutting to what looks like a particular process, you're going to get very different predictions. The second issue is that if you have some mismodeling in something other than mech, and then you cut before you tune before you cut, your tune is going to fail because you're adjusting the different amounts of the processes when you cut. So you certainly need to tune post-cut. But again, that discrepancy is still larger than your new physics. So we can do sort of a.
Oh, sorry, just don't really understand the logic because you mentioned so many times the tunes, right? So I only have one data set, right? So for experiment, I have some neutrino energy, which I don't precisely determine. I measure some events as a function of PTOS and something else. So I compare with what I expect using a generator, right? And obviously mismatch because my generator is not perfect, right? So I do a tuning to match the data. You are saying in presence of new physics, even if I do a tuning to match the exact same data set, I still won't match. So I still see a residual of new physics behind.
So this,
that means whatever tune I'm doing, maybe you only tune the Mac component that only changes some part of the space. I still have residual of EXL.
So this is a disagreement just between the two standard model generators here.
I understand,
Yeah.
but what's the tuning here? I'm tuned towards the data I'm going to observe.
Yeah.
And I won't match it because there's new physics. And I constrain how much tune I do. Essentially, I only tune certain components of the cross section. Is that the?
So yeah, so I passed over this for time, but basically what happens for this case is sort of like in the sterile neutrino case. You're not tuning away the new physics. So when we're doing this analysis, our concern was you want to adjust for cross-section mismodeling. But if you do this tuning procedure, you do risk just tuning away the new physics because you're saying this is my expectation, but it's exactly the data you're looking at. In this case, it turned out that actually you don't tune away the new physics. So this is the case where we tune post-cut. And when you apply the tune, you do sort of reduce the strength of your new physics signal. That's the black points relative to when you don't do a tune, that's the red points. And the reason, again, came back to this distribution in the tune plane. So in this case, what you have is that your standard model is post-cut is sort of localized to a particular region. And then our new physics signal was kind of populating the whole range. So you're not tuning away all of the new physics. And that's sort of what you see here. You shift the region a little bit, but you still have some sensitivity to new physics. So then the question becomes, once you have this mismodeling, can tuning kind of save you from that mismodeling and leave you still with some sensitivity to new physics? So that's where these two tune lines are really coming into play, is how much can this procedure actually help you with your analysis? And the answer turns out to be, it still doesn't save you completely from mismodeling, because when you're doing these cuts, these generators just disagree so much based on their final states and on the fact that they have different contributions from the different processes, basically. Does that answer your question?
Yeah, that's
Okay.
but if I'm playing devil's advocate,
Yeah.
say, of course, you're only tuning one parameter. You have so many measurements. I would tune multiple components simultaneously. I could absorb here.
You mean like different processes?
Yeah. Just like the plot you show, there's different process contribute differently at different times. Just like you know, I think PCI is huge. There's a huge number of parameters to tune, for instance.
Yes.
So you can do that here. I can absorb everything.
Yeah, so I think the more that you tune, the more you would risk tuning away your new physics as well. So here we're just following Nova's procedure because that's one example of a procedure that is actually used in not in a near detector analysis, but in an experiment. So this is how they account for cross-section mismodeling, at least.
But do you foresee the Nova tuning procedure will be the standard of our future?
No, I think every experiment decides to do something different. So it's something that we want to look at other experiments approaches as well and see how those fare. But this is just the first one that we had available. I will say Nova is actually changing their tuning procedure a little bit for future analyses. That's something that one of the grad students is working on right now. And what they're going to do is reduce the number of degrees of freedom that they have, basically. Okay, so just to look at what this looks like if you try to do sort of a nonsensical sensitivity analysis, because as we could see, our mismodeling was so much larger than our new physics. But just to illustrate what would happen, on the left we have the case where you don't input any new physics and you just do standard model to standard model. And again, this gray region is sort of our truth region where we used the same generator for both model and data. And then this is where you have some mismodeling. And it actually does successfully conclude that there's no new physics. The problem is that if you then add some new physics, you once again conclude that there's no new physics. And we checked this, it even concludes that at 5 sigma. So I will note that this is an analysis where we really had to come up with a rough covariance matrix. It's not one that they would actually use, but it at least gives an illustration of how much this generator mismatch is dominating over your new physics. Okay, so that's just a conclusion for the mononeutrino case. So I'll just wrap up. So cross-sections are an important part of how neutrino accelerator experiments interpret their data. And when they do standard model analyses, they employ a procedure called tuning. And we want to understand all the impacts that procedure may have. So we looked at a near detector new physics analysis. And if we look at a sterile neutrino case, which is sort of a modification of the overall event rate, you can survive the tuning procedure, but there will be a bias in your interpretation of the new physics that's coming from this modeling. And then if you look for low rate physics where you have to apply some final state cuts, you basically can completely lose sensitivity because your generators react very differently to those final state cuts. And again, you can think of that as a proxy for how well we can model nature. So basically we need better theory predictions and also hopefully some better experimental solutions in the short term to try to unlock the full potential of these neutrino experiments. Okay, and that's it. Thanks.
Yeah. Do you have any more questions?
Yeah.
Just regarding whether or not you would tune away the new physics, does that mean there's a strategy where you can choose the parameters in the generator to tune such that you know the specific kind of new physics you're searching for would not be tuned away by this combination?
I think there is. I think experiments are extremely nervous about doing a tune like that. So I find it unlikely that they would do that. The nice thing about, say, a sterile neutrino analysis is that you're already not correlated with the tune parameters.
Yeah.
But I think in general, experiments would be less inclined to sort of do a different tune for each analysis.
Why would that be? So is it just computationally expensive? Or?
I think it's that it's sort of like a level of arbitrariness that goes into that. Yeah.
So Raymond, if you pay me enough money, I with data and the tuning, I will give you arbitrary significance in the signal you want.
Yeah.
I can do that. I guarantee you.
I see.
You can tell me a bunch of new physics. I know I can work on how to tune.
You can find any new physics you want. Yeah.
All the data.
Oh, I see.
Are like if you were at lower energies, are like cross sections better understood there? Like, I guess I'm not sure what I would expect reactor neutrinos might be at lower energies. Like, are those experiments less susceptible to this modeling?
Yes, I think you also have experiments that have, I want to say, electron neutrino scattering, and those are significantly more under better control. So not every experiment suffers from this exact problem, but for an experiment where you have neutrino-nucleus interactions at like the GeV range, you're going to run into this. So something like Dune will run into it as well. Yeah.
With the energy, I mean, reactors.
Yeah, reaction.
Yeah,
Like there we don't know flux.
Well, I mean, couldn't you do the same thing, do like a near and far vector to figure out?
No, but
The answer is you could. And there's a set of neutrino, like a reactor neutrino experiment trying to determine the oscillation parameters. Like actually, theta 1 strip discovered in the reactor. But the upgraded version has to detect it. All right. And actually, the fact that with one detector you can discover theta 1 strip already tells you have reasonable control of the flux. Because we know the power. The power is from the nuclear reaction. When you know the flux is reasonable amount. But you can do you want I see, but can I ask a different question? So isn't all this you're doing telling us we need the better neutrino-nucleus cross-section calculation?
Pretty much.
Because the tuning is actually ad hoc. It's a strong bias, strong assumption, and you're relying purely on the luck that
Yeah,
the
exactly.
tune I choose that either way might be some signal, right?
Yeah.
So how many people are working on it?
People are working on it. I think some of the Fermilab people are also involved in creating a new neutrino generator as well. I don't know very much about it. But I think, so in the short term, one thing to do is consider what types of new physics don't have final states that look like just a neutrino-nucleus charge current or neutral current interaction, because what we were looking at here is all neutrino-mediated new physics. And so that's like sort of the worst case scenario for how much you'll be impacted by mismodeling. So I think SBND is looking a little bit at sort of new physics, say coming from meson decays and stuff like that, where the final states are E plus E minus or 2 photons, and it just should have a much lower sort of charge current neutral current background that has mismodeling inherent in it. Yeah. So for me, I think that's the most optimistic short-term route.
Yeah, that's a robust short-term route.
Yeah.
I will depend on this cross-section.
Also, maybe you said it, but is there a motivation for that second model you were talking about?
The mononeutrino?
Yeah.
Yeah, so it's it can be connected to neutrino masses as well, and it can be a dark matter portal. So it's just like an interesting model where you can kind of have a connection between neutrino masses and dark matter. I don't know all of the details of this model, but it's just like a neutrinophilic dark matter example.
Dark scale.
Yeah.
Yeah, thanks.
Yeah.
Oh, yeah. No, I think it's